IPv6 is really big, 128-bit size, which can provide sufficient amount of address to identify in the internet. Nowadays, when we take a computer, inside that physical computer, we get many VMs, virtual computers, virtual machines. So for you to look at this one physical computer, but for someone in the internet, the traffics are coming from 6 different computers. This is computer number 1, 2, 3, 4. How? Here, logically, they are separated as 6 computers. They have their own MAC address, own IP address, own IP stack, the layer, OSI layers, etc. So, in today's world, because of virtualization, cloud computing, etc., we need many IP address on a single device. Not just one IP address like you have today in your laptop. Many. If you have VMs in it. If you take a server, no, even today, if you take a server, we'll have 10 computers, 100 computers inside one server, used by 10 different people. For each VM, there will be a separate resource like hard disk, RAM, CPU, IP address, MAC address, cache memories. Everything is allocated for each VM uniquely. They're independent of one another. So IPv6 is very useful when we do such virtualization. Now all these PCs can be public. In IPv4, because we don't have enough IP address, we have private scheme and public scheme, and we do something called NATing, which is going to be our topic in coming days. But in IPv6, there is no need for NATing, as I said earlier in the previous class. There is no need for translation from private to public. That is where NATing comes into picture. Translation from private IP to public. Fine. Now let us move on to the newer portion. When we were talking about addressing, we saw unicast, multicast, and anycast. What is unicast? Address, correct. Address that identifies a single device. Unicast. Address given to a particular device. Any traffic to that address goes to a particular PC, not to many. Example, this computer's IP address is 2001::1. And there is a router here on this port F00 2000:2001::2. So I may have multiple devices connected through a switch in the middle. I may have a switch, and I may have multiple devices. but they all have a unique address called unicast address. So when you send a traffic to 2001 colon 2, it only goes to router, not to the other two computers. It's unicast. And this can be a computer or this can even be a router. Let me change it to a router so that I can explain you multicast. Router 1, router 2, router 3, router 4. Now, traffic is going from one device to another using unicast. But what if I run a protocol like OSPF? If you run a protocol like OSPF, you will definitely see a multicast also involved. As I said, the multicast address FF02 colon 5. This multicast address gets added to the device when you enable OSPF. When we enable OSPF on this port is not only having this address, it also automatically gets this address. Likewise here. So when we enable when we enable OSPF, you can see multicast getting enabled automatically. And depending on the protocol, the multicast address will vary. If it is OSPF, FF02 colon 5. So that when a single hello packet is sent, it will go to everyone. You should not think like this. How can a single packet go to everyone? Okay, it may go to R2 and then say, hi, R2, how are you? And then come back, go to R3, hello, R3, hope you're doing well. And then come back, go to R4, hello, are you okay? No, that's not the way. When we say it goes to everyone, how can a single packet go to everyone? When it is sent to a switch, because it's a multicast address, a layer 2 multicast address will be assigned automatically to the packet. So when switch see the layer 2 multicast address, it will forward the packet, a copy of it to every wire. I repeat, a copy. Duplication happens on the switch. When the packet arrives to the switch with this layer 3 multicast address and layer 2 multicast address, that is also auto generated. We no need to uh, think about that. It is taken care. And when when the traffic hits the switch port will immediately forward the traffic via all the ports. A copy is going simultaneously to all the other three routers, R2, R3, and R4. And if R3 is running OSPF, then R3, R3, R2, and R4, if they are running OSPF, only then they can open it. See, switch will send to everyone. But can R2 open it? It can open only if it is a member of FF02 : 5. Is it a member? Yes, because I enabled OSPF on F2, sorry, F00 on R2. F00 is now eligible to open it. Is eligible to open it and process it. That is multicast. See, advantage is R2 is not sending 3 copies. It is sending only 1 copy of a packet. And it gets multiplied depending on how many devices connected to the switch. That is why it is called as multicast. So that this R1 need not to generate many copies. And bandwidth is also not consumed here much. It's only 1 copy going. Yeah. So it is good. Multicast is good. Next, what is the anycast? One to the closest. One to the closest. The nearest one. The nearest one. See, let's take an example. You want to withdraw some money from an ATM. And this is your house. Now, you try to locate the nearest ATM. Let's say this is the nearest. You go to the ATM and you see a board hanging there. Closed. ATM closed. But when you started from here, you were thinking only about this one ATM number 1. But the problem is it is closed. Now you start thinking about the next location, next nearest. It's here. And you go here now. And now you take the money from the machine. This is what called as anycast. See, ATM is the destination address, ATM. Is the destination name changed? No. I want to go to ATM. You went here, but this ATM is closed. With the same name only, you are going to ask, is there any other ATM close by? Then they say, okay, go here and take right. Now you come here and take the money. You see? The destination address is same, ATM. But if this is open, you will be taking money from here. If this is not opening, if this is not open, then you will be taking money from here. Though their original address can be different. This is Thandayarpet. This is Rayapet. சத்தியமா இதெல்லாம் எங்க இருக்குன்னு கூட தெரியாது. ஆனா பேர் மட்டும் தெரியும். சென்னையில இருக்குன்னு மட்டும் தெரியும். So there is Rayapet, Thandayarpet. That is different, but ATM name is same, no? What I'm trying to say is This computer will have one unique IP address, 2001 colon colon 1. This computer may have another address, 2004 colon colon 1. But the anycast address for both will be same, like 2025 colon colon 1. Here also 2025 colon colon 1. This address is same. So your routing table will show you the nearest one. It will always show the nearest one, no? Routing table. When this goes down, your routing table will show the next nearest for this 2005 colon colon 1. That is why those addresses are called as anycast address. You can see same address in multiple device in different location, so that the routers can use the nearest one, first nearest. If that is not available, the next nearest will be seen in the routing table. This is what we call as anycast, one to the closest. For example, DNS, domain name server, no? Google's domain name service 8.8.8.8. With this IP address, same IP address, many DNS servers are around the world. So if you are in Chennai, you will be going to the DNS which is closest to Chennai. If I am in Bangalore, I will be going to the nearest closest DNS. But both IP address is same. Anycast address, even if the address is same, it won't conflict. It will not conflict. Did you understand anycast? One to the closest. Okay. In IPv6, you can give any IP address and say, I want this to be a anycast address. We can configure. All right. So far, we have seen the three type of addresses. One is unicast, example FE80, and any address that is starting with 2000 series. These are unicast address, but this one is unicast link local. We won't use this to communicate. This is for devices to discover one another. Any address that begins with 2000 is what we use for communication. Sometimes someone may ask you this question. What is link local address? The link local addresses or unicast address begins with FE80. Only this phone number you need to remember, FE80. The rest all will be different. FE80, and this address is used for neighbor discovery. Neighbor discovery is to know who is connected next. In IPv4, we were using ARP to do neighbor discovery. That is how we learned the MAC address of the neighbor. In IPv6, it's link local address. That's the reason I was telling you there is no ARP. Link local address. Now this address starting with 2000, it can be 2000 or 2001 or 2002, 2003, whatever, can be anything. If it starts from 2000, it is called global unicast address. Global. Now, this is the address that we will be using for communication. And there is no concept of private. That is why it is called global. No private, no public. All are public only. But we don't use the word public. We use the word global. Global unicast address. Link local address. Global unicast address. Global. The address that we use to ping, we got link local address, which is used by the devices to discover. Even a computer can discover a router. Router can discover another router. Okay. So discovery is through link local only. Yeah. Right. Next is, okay, this is another question they may ask. Why 2000? Why not 00001? Why it didn't start from 1? Or why not 1001000? Why it starts from 2000? See, in the year of 2000, some of few might have not even born. In the year of 2000, this became standard. IPv6 became standard. In order to remember that, starting from 2000 is what used. Yeah. So that may be a silly question, but you will come across such question. Yes, you will definitely come across such questions. Some people ask. Okay, so you know the answer for that now. Next is, we say it is 128, but you know how it is divided? First 64 bit is called as global prefix. And the last 64 bit is called as interface prefix. You see, in IPv4, if it is class A, we will say first octet is network, the other three octets are host for class A. In IPv4, we used to say like that. We used to say like this in IPv4. But in IPv6, we don't have classes. No class A, B, C, nothing like that. Now your next question may be, do we have subnetting? We do have, but it is not that big subnetting as you had in IPv4. Subnetting means, it's a very joyful thing for Priya. Calculation, she is a mathematician here. She wants calculation things. But sorry, Priya, you don't have that mathematical fun here. It's easy subnetting only here. Now, instead of calling as a network bit, the 64-bit is called as global prefix. We don't call this network bits or network prefix, global prefix to identify the network. And here we don't call it as host ID, we call it as interface prefix. I hope now you understood what is interface prefix and global prefix with the light of IPv4 network ID and host ID. Fine. So we got 64-bit of network portion and 64-bit of host portion. But the name is different. Now, if that 64-bit, if you write in binary, it will be too big. That's why IPv6 is written in hexadecimal. Hexadecimal meaning what? Hexa, 1 bit is equal to 4-bit of binary. How? In hexa, this is the biggest number, f. F is equal to 15. To write that f in binary, if I put 1 here, will it be 15? No. I have to put all 1. Now I'll get 8 plus 4 plus 2 plus 1, 15. So if I write in binary, it is too many digits. If I write in hexa, 4 times smaller it will become. That's why we are writing in hexa. So 128 binary bit. When you write in hexa, it becomes 4 times smaller, right? 4 times smaller. Here 4 digit, here only 1 digit. What is 4 times smaller? 128 4 times smaller means what? If you divide by 4, what you will get? Tell me what you will get. 32 or 62? Very good. 32 hexabit. See, IPv4 is also 32-bit, no? But that is binary bit. This is 32 hexabit. Okay. Now what they did is, this 32-bit hexa, if it is continuous numbers, it will be difficult to understand and use it. So again, this 32-bit is grouped into 4 bits. 2, 3, 4, 5, 6, 7, 8. This is how it is grouped. For example, 2001, 0ABC, 1004, 2, okay, 3210, EBAB, something I'm writing. Okay, 1059, 8121, 0001. So we can see here 128-bit is written in 32 hexabit with 4 hexabits in each group. How many groups in total we have? 8 groups. See, there is a lot of connection here in IPv4 and IPv6. In IPv4 also we have 32-bit. Here also we have 32-bit. But there it is decimal. Here it is hexa. In IPv4 also we say 8-bit per octet. Is it 8, 8, 8, 8? This is IPv4, 8-bit per octet. Here 8 groups 1, 2, 3, 4, 5, 6, 7, 8. 8 groups of 4 hexabit. This is called hexadate. 8 hexadate you have. IPv4 is 128-bit written in 8 hexadate. The first 4 is global prefix. The last 4 is interface prefix. So what is the binary equivalent of this? It is 64-bit. This is another 64-bit. Did you understand this so far? Okay. Now, 2000 colon 0000000000000000 A B C D 0001. Let us take this as an IPv6 address, for example. I have 8 hexadate here. Now, do we need to write like this, or can we write it in a very short form? Yes, you can shrink it and write it. How? You see, this is 2000. Can I cut the zeros? No, I cannot cut the 0. It will become 2. The value changes. I cannot cut the 0. So 2000. Instead of writing these many zeros, you can put 1 0, again 1 0, and the 0001 can also be written as 1, no? Because the 000, is there any value? No value. No value at all. That need not to be written. See, this 0 I cannot remove. But the leading 0 you can remove. Leading 0 can be removed. And then 0, 0, A, B, C, D. This leading 0 also can be avoided. You see, the address is now shrinked. Even further, you can shrink it. How? Like this. 2000. You see, continuous zeros, no? You can just put colon, colon. You no need to even put 1 0 inside. And then 1. But because you have already done here, you cannot do it again. Again, you cannot do it. Only once you can do that. So now we will give this to the computer, not this one or this one. If you want to give like this, you can give. You can give like this, but in the questions in exams, if they ask you, you should give the best answer. This is the best. All three are same. All three are same. But which is the best way to write? This one, because this is short and sweet. Best way to write. Right. So when you write this to a computer knows how many zeros to put here. How you know? It knows there should be 8 hex date. 1 is here, 2, 3, 4, 5, 6 is there. So it knows that the other 2 hexadecimal of 0 will come here. It knows. That's why I cannot do it twice. I should do only once. Either this you can shrink it like this, or this can be shrinked. Any one. Cannot be both. Okay. So when you write this one, your computer understands like this. Easy. Now let us talk about subnetting. Subnetting is also very easy. Let's say 2000 0040. Let's say this is given, and then 0091. This is your network given to you. Now what you can do is this 16-bit, you can put some number and make it as a new subnet. Understand? I told you the first 64-bit is global prefix or network. First 64-bit is global prefix. In that, only 48-bit they have given you. The remaining 16-bit, you can add some number and form new networks. For example, here how many bits we have? In binary, 16-bit. See, 16 multiplied by 8 is 128, correct? This is 8 hex state. We just now saw those things. So now you got 16-bit. Oh, you know what? 2 to the power of 16. 65536. These many subnets you can make from one network. How? This is /48. They have given only 48-bit. By doing like this 2000 colon 0040 colon 00091 colon 0001. This is first subnet, 64-bit. For the second subnet, I'll put 2. Again, these leading zeros you can avoid. All right. So subnetting is that much only here. 2000 colon 40 colon 91 colon 3/61. This is first subnet, second subnet, third subnet. Fourth subnet will be 4. Go like that till it becomes F. And then you put 10. 10 colon. That goes like that. Subnetting is so easy. because you got 16-bit reserved only for subnetting. In IPv4, there was no reservation. We have to borrow. That is why the calculation was too much difficult for us. But here you are not going to do any calculation. You need to simply increment the bit in order to get new subnets. Is that clear? All right. Tomorrow what we are going to do is we are going to do a small lab in IPv6. We'll be doing like 4 labs. We'll do first 2 labs tomorrow. First lab will talk about how to assign IPv6 address and how to verify how the neighbor discovery happens using link local, those things. The second lab will be static route and default route in IPv6. The third lab will be routing protocol, RIP, EIGRP, OSPF. Right? And then we will do some interesting topic called IPv4 to IPv6 tunnel. These are things that are yet to be done in IPv6. So we'll see tomorrow.